Okay, what kinds of questions do we have? Remember, you have to unmute if you're gonna talk.
I know that we've talked before about like it not mattering if we're in ortho or para positioning, but is there any case we're gonna have on our exam where it will matter?
Run that by me again.
For the ortho or para positioning on the cyclohexane, I know we've talked about there's the select few on the chart that will be in ortho or para position. Will there be any cases that we'll have to do on the test where it will matter if it is in the ortho or para, or it doesn't matter?
Well, so so if I give you a reaction, or if you're doing well, two different situations. If I give you a reaction where let's say I have an OH group and I say, well, go ahead and add a Br2 and an FeBr3 to it, I'm going to ask you to write both the ortho and the para products. So I'm going to ask you to write both adding the bromo ortho along with writing also adding the bromine in the para position. Now, if you're doing a synthesis, so if your goal was to add the bromine either ortho or para, what in a synthesis problem you can just write down whichever product you want. But if I'm giving you a reaction, I'm going to ask you to do that. I think one of the cases that we've already invoked for sterics has been if you have, let's say I had that OH group and I wanted to do some sort of blocking on it. So if I want to do blocking, what we've said is that if you add something large like an SO3H plus group, that it will automatically go to, we're going to say that nearly 100% of the product is going to be adding to the para position, because that's what allowed us to then add the next group to the ortho position. So if you want to invoke sterics in a synthesis, that's perfectly fine. But in a synthesis, you're going to be allowed to pick and choose whatever product, ortho or para you're going to use for the next step. But up here, when you're doing basically when you're writing the product of the reactions, then I'm going to say write both the ortho and the para products. Does that help?
Yes, thank you.
Dr. Nichols, will the exam on Friday include the information from today's video about aldehydes and ketones? And if so, or I guess regardless, can we go over the formation of an acetal or a ketal?
Yes, and a yes, it will. So it'll be up to and including today's lecture.
Okay.
Wednesday's lecture, in dangerous territory here because it won't, while it won't be on the exam, I'm going to put it up and it'll be the replacement lecture for Wednesday, which if it's not on the exam, I could very well see people waiting till Monday to ask about it, which is perfectly fine. So for when we take an aldehyde or a ketone, and I'll take the ketone today, I'll do that one. What I want to do for this ketone is I want to add something like methanol to it. Now we did, just in context, we took our ketones and we added to those Grignards, and we also added H- because H- came from either lithium aluminum hydride or it came from sodium borohydride. So we added strong nucleophiles like the Grignards and the H- to the carbonyls, and those would come in and attack the carbon and have the pair of electrons move up to the oxygen. And then we would form our O- while either adding the R or adding the H group. And then the O- would try and bring the pair of electrons, it would try and bring its pair of electrons back down to reform the double bond, but in this case, with either 3 alkyl groups or 2 alkyl groups and an H, there's nothing that'll leave, so it just kind of hangs out until it gets protonated by H+, and then form the final product. So we would end up either forming the carbon-carbon bond, which would have been the Grignard, or we ended up reducing the carbonyl down if it was H- from lithium or sodium borohydride. What we're doing in the next chapter is we're not adding strong nucleophiles like R- and H- because they have no problems. They're already strong nucleophiles. What we want to do is we want to add a weak nucleophile. And if we add a weak nucleophile like an alcohol or like water, the problem is they're not strong enough to add to the carbonyl directly. So instead what I need to do is to make the carbonyl more electrophilic by basically adding acid to this and protonating the carbonyl oxygen. So if I protonate the carbonyl oxygen, I'm going to end up with that oxonium ion. And that oxonium ion has a resonance structure where I take and I can move the pair of electrons from the carbon-oxygen double bond and I can form the carbocation. But by adding basically the resonance hybrid of that, So these are my two resonance structures. The resonance hybrid would be to have a partial bond to the oxygen, a delta plus on the oxygen, a delta plus on the carbon. Those two delta positive charges have to add up to +1 overall. So what I did was, by adding the H plus to the carbonyl, I made that carbon more delta plus, and basically I made it more electrophilic, more electron poor, so that now my weak nucleophile, namely my alcohol or my water, can come in and add to that carbonyl group. Or if you want, you can write the resonance structure and have it directly come in and add to that carbocation. So I'm going to change colors here. If I take my methanol molecule and I add it to the carbonyl, then the pair of electrons would go up to the oxygen. If I do that same reaction over here on my carbonyl, it'll just come in and add to the carbocation. So the point of adding the acid is it's going to make this carbon of the carbonyl, it's going to make the carbon more delta positive, which means that weak nucleophiles can add to it. And if you come over here to this resonance structure, then we already know that weak nucleophiles will add to a carbocation. So without the acid, I wouldn't get any reaction. So if I, either way I do this reaction, I'm going to get the same product, which is the OH and then the O with the methanol, the O of the methanol added to the carbon. So I'm going to end up with this species, which is brand new. We haven't written this kind of a molecule before. Okay, everybody with me? If you are, somebody unmute and say yes.
Yeah.
Okay. So then the next step in this mechanism would be to take and lose the H plus by moving the pair of electrons to the oxygen. So I'm going to lose an H plus here, and I'm going to form my CH3, OCH3. Okay. So this reaction occurs when I add one equivalent of methanol to a ketone or an aldehyde. And so depending on whether this molecule came from a ketone or an aldehyde, this number one is called a hemi, and it's a hemi, in this case, it's a hemi-ketal, because it came from having two alkyl groups attached to what was the carbonyl, so it's a ketone. If one group was an H and one group was an alkyl group, it would be called a hemi-acetal because it came from an aldehyde. So we're basically like halfway there. Right? Everybody still kind of with me?
Yes.
Yes. I have a question.
Yeah.
So would you tell us that we only had one equivalent, or if you didn't put two equivalents, we assume that there was only one equivalent?
I'm going to be very explicit in terms of telling you whether there's one or two.
Okay.
So this would be the end of the reaction if there was just one. But now I'm going to go to the next slide and pick it up from here to get to two. So let me save this slide and let me rewrite that structure on the next one. Okay, so oh, sorry, that's an H. So we don't need to add any new acid because when I lost the H plus on the previous slide, that H plus is still there. So if the H plus is going to protonate one of these two oxygen species. So if the H plus protonates the OCH3 from what you just wrote down, that basically is the previous structure and everything would go backwards to the beginning. So what I need to do to go forwards is I need for the H plus to protonate the alcohol. So now I'm going to make my oxonium ion. And what happens next?
We get rid of we get rid of the water.
I'm going to lose water. And I'm going to form a carbocation. And now the second equivalent of methanol is going to come in and add to the carbocation. And remember, it's the entire methanol, so I'm going to add the whole thing. And now the last step is to
Get rid of the hydrogen.
lose the H plus. Like we've done whenever we've added a neutral nucleophile like an alcohol or water to a carbocation. So notice what I'm doing is I'm regenerating the catalyst of the reaction so that the H plus is used, but then it's regenerated at the end. So then when you have two OR groups, you're either an acetal if you came from an aldehyde, meaning that there would be an R group and an H group, In this case, this one is a ketal because it's got two of the alkyl groups and came originally from the ketones. So this is the full-blown ketal, whereas over here, this is half a ketal, so that's why it's called a hemiketal.
Dr. Nichols, for this reaction, would we need to have like the equilibrium arrows for it, and why would that be?
So that's the next thing. If we just let's start at the end here. Now we know that if I had this molecule with my two oxygens, if you added acid to that, the first thing that we would do is, right, because I'm in class and I'm going, okay, what's the first step? And you would say, someone would say, protonate
The oxygen.
Protonate the hydrogen.
protonate the oxygen with the H+. So if I add H+ to this molecule, the first step would always be protonate the H+, or protonate with the H+, protonate the oxygen. And so what would I get? I would get this molecule up here. So we write an equilibrium arrow because now I'm going to end up here. And then if I had this molecule with the plus charge, with the oxygen with the plus charge, what could happen here? Well, I could lose the methanol and get the carbocation. So then we need an equilibrium arrow this way because this reaction could go backwards. And then if I had the carbocation and I reacted it with water, we could go backwards this way to add the water to the carbocation. And then if I had an oxonium ion, we could go backwards if I lost the H+ to give me the hemiketal. And for the other reactions that we did before that, we would write equilibrium arrows in there as well. So overall then, if I write the final reaction, if I take a ketone and I add two alcohols to it, it's going to be an equilibrium. Acid is the catalyst, so it should go over the equilibrium arrows. And I would end up with the ketal, or sorry, the ketal. And water. So overall then, this is an equilibrium reaction. Does that make sense?
Yes.
Can I ask an unrelated question?
Sure.
So like there was a quiz question. I went through my notes to like double check, but when we were making or when we were adding esters to a benzene ring, are we using like different reagents in a different sequence if the carbon is what's attached to the ring versus the oxygen?
That is a good question, because somebody just did that. Somebody just did it the wrong way on one of the quiz question for today. So let me, there are two different sequences or two different sets of reactions. If you want to take a benzene ring and add the carbonyl group to the ring versus if you want the oxygen, if you want the benzene ring to be the alcohol part of the ester. So in order to understand the difference here, if we want to make the ester this way, I need to take the carboxylic acid and react it with the alcohol with H+. And that's our Fischer esterification. If you want to make the ester this way, you need to have the OH group attached to the benzene ring. And react it with a carboxylic acid. It's still Fischer esterification. So it's important that you get the right molecule or the right group on the ring. But there's two different ways to do that depending on whether you want to make the carboxylic acid or the alcohol or the phenol.
So for today's lecture material, how would you ask about that on like a quiz or a test?
Which problem?
When we just made the acetal and the ketal.
I could ask two ways. For the acetal and the ketal on the I guess at this point on the exam, I could say, first of all, write the product of adding one or two methanols with an aldehyde or a ketone with H+. So in other words, I could say, write the product. The other way I could do that is I could ask you to write out the mechanism. If I'm going to ask you to do the mechanism, it's going to be with two equivalents of an alcohol.
So would you ask us to identify if something is a ketal or an acetal or a hemi, or would you not ask that?
I could ask that.
Okay.
To be honest with you, I might hold off on that until the fourth exam.
Okay. Thank you.
Because today we started with hydrates, acetals, ketals, and hemiacetals and hemiketals, but there's going to be a number of those other molecules, so I might ask all of those together. So I probably would hold that off until the next exam. What else?
Can we go over Diebol as a reagent?
Sure. So that was for today as one of the potential reagents. And in this case, it is a way to make it's a way to take an ester and reduce it to an aldehyde. Is the reagent called Diebol or Diebol. And we're going to talk more, we'll talk about this mechanism in detail in chapter 24. But the idea is that if I have an ester and I was to try and reduce it with lithium aluminum hydride, you know, and then my H plus H2O step, what I end up doing is I end up reducing the carboxylic acid part down to an alcohol, and then it splits apart and I end up with the alcohol part. remember an ester is made up of, and you know this from lab, we took a carboxylic acid and we react it with an alcohol part. So when you make the ester, this part came from the alcohol and this part came from the carboxylic acid. So if we try and reduce that, we're going to split it apart and make two alcohols. But what Dibal does is Dibal basically replaces the OR group with an H. So this is a very strong reducing reagent, and this one is mild. It's a milder reducing reagent. So Dibal is I wrote it this way. I think I wrote it this way in the notes. I think I'm missing a carbon. It's diisobutyl. So this is an isobutyl group. So there's two of them. So it's diisobutyl aluminum hydride. So part of the reason why the ester gets reduced all the way down to the alcohol in the primary, and the primary alcohol on this side, and that splits apart, is because the lithium aluminum hydride has up to 4 H minuses. With Dibal, there's only 1 H minus, and so that 1 H minus ends up only replacing the OR group. And we'll get into the mechanism of that in chapter 24. So right now it's a reagent that we can use. This is a reagent that we can use to prepare aldehydes from esters. That's all it is. What else do you have?
I'm not sure if you've already done this, but is there like a specific topic list for the exam, or is it just like the list of aromatic reactions that you have?
It's going to be the list. of, well, let's see. It's going to be the list of aromatic reactions that I have, but I also believe, and I'll have to put that together, although with this being kind of an open note exam, I mean, in theory, there's the list, it's going to start where we left off. And so what we did before we went into electrophilic aromatic substitution is, and I didn't put these reactions on there, but we were able to convert, right? We were able to react the benzene ring and remove the aromaticity, which was called Birch reduction. I don't think that was on the last exam. I don't think that if we had a alkyl group attached to the benzene ring, that if we wanted to free radically halogenate the benzylic position, if we want to free radically halogenate that I don't believe was on the last exam. Taking any alkyl group and converting it to the carboxylic acid with the CaMNO4 oxidation, that wasn't on the last exam. So those kinds of reactions would also be on this exam, and I didn't include them in the list of transformations because that list of reactions that I put in Friday's folder are particularly helpful for those, for like the synthesis, when I say take a benzene ring and make this out of it or some other molecule. Although, to be honest, the CaMNO4 oxidizing the alkyl group, that's something that you have to do if you're going to put a carboxylic acid group on the ring. It's one of the ways.
Thank you. And also, is there like specific mechanisms that we're gonna need to know as well? I know you just mentioned one like a couple minutes ago, but other than that,
I mean, I could always ask you to take any kind of substituted benzene ring. So maybe I could say react this with like a Br plus and add that Br plus to either the ortho or meta or para position, and then draw out all the resonance structures. And then the final product. And that's that would be in the video that we started this last Monday. So that's a mechanism I could ask you along with nucleophilic aromatic substitution. I'll have to come up with a list of potential mechanisms.
thank you.
But I mean, if it was in the video, if it's been in a video, it's fair game. Any other issues?
I don't know if you saw this one, but someone said in the comments, could we go over oxidative cleavage or terminal alkene oxidation?
Is that in the chat thing?
Yes.
Yeah, unfortunately, I can't access the chat while I'm showing you my screen. So let me save this again just to make sure. And let me, okay, what was it again?
Could we go over oxidative cleavage or terminal alkane oxidation?
Terminal
Alkene, sorry.
alkene. Okay. All right. So you'll notice that terminal alkene oxidation is not in the reactions for today to make aldehydes and ketones. And there's a good reason it's not, because if you want to cleave this, a triple bond is really stable. So you need to go with CaMNO4 and heat. And when you go with CaMNO4 and heat, you turn both of those you turn both of the carbons into carboxylic acids. And this one, when it's terminal, you turn it into carbonic acid, which becomes CO2 and water. So you can't form an aldehyde or a ketone with either a terminal or an internal alkyne. But if you're going to cleave a double bond, you can turn that double bond into a ketone and an aldehyde. The hint here is that you can't use CamNO4 because CamNO4 would convert the aldehyde into a carboxylic acid. So there's another way to do this oxidative cleavage. In order to cleave the double bond, but then just keep this aldehyde the same. And since that one is in the, since that reaction is part of the or is part of the quiz for Wednesday, the hint I'll give you is, should be in your notes from last semester, but also I think it's, well, all the reagents that I've asked you in the quiz for Wednesday, they're all in the Top Hat textbook. There's another reagent that you could choose whether to keep the aldehyde as the aldehyde or oxidize it to the carboxylic acid. And that's the one you want to use with this problem.
If the H on the double bond was another R group, would we be able to use CamNO4 in that case?
Yes.
Okay.
Yes, CamNO4 would work if you wanted to cleave this. If you wanted to cleave that and form two ketones, then you can do that to make two ketones. So that would be okay. Is there anything else in the chat questions that I can't see?
No.
Because I don't see. That's one thing I haven't yet figured out how to do, is to see the chat while I'm in the whiteboard mode. Unless I do this, but that's not even helpful. Anything else? I'm going to be grading the, I'll be grading the quiz problems that you submitted. So if up to a certain point today, and then after that, I'll grade them first thing in the morning. So you'll be able to see what your quiz, as you're submitting those syntheses. So they'll either be graded. I haven't put the scores in, but I'm grading them as we go, so. Anything else? If there is, throw it up on Piazza, email me. You can set up one of these one-on-one or small group meetings, or anything from today's video we can go back over on Wednesday in either of the 2 meeting sessions.
Thank you.
Okay.
Thank
For
you.
those of
Bye.
For those of you in Ohio, you're going to be locked down tomorrow, so hopefully everybody will be surviving. Oh, there's the chat.